Let me try to share my screen.
Excellent. Okay, fantastic. So great. Let's welcome our next speaker, who is Mary He from the University of Toronto, and she will be talking about a Riemannian metric on hyperbolic components of the Mandelbrot set.
Thanks, and thanks to the organizers for organizing this wonderful conference and for the opportunity to speak. It's really great to see so many familiar faces. So today, I'm going to talk about a construction of a Riemannian metric on hyperbolic components of the Mandelbrot set. So since my talk is the first talk of the day in complex dynamics, so I will start, So I will start by telling you.
So Mary, sorry to interrupt you. Did you move on to the next slide?
Yes, so my slides are not.
We cannot see it, yeah.
Let me, so can you see now?
Yes, we can.
Okay, cool. Yes, thanks. So, right, so I'll start by telling you what is a quadratic polynomial and what is the Mandelbrot set. So you will probably hear more complex dynamics in Kashar's talk after me. So we consider a degree 2 complex polynomials from the complex plane to itself. And any such polynomial is a fine conjugate to z squared plus c, where c is a complex parameter. And as dynamists, we're interested in iterating the dynamical map. So that is to say, we want to compose fc with itself again and again and again. So when you start to compose z squared plus c with itself, you will see that the composed map, the degree of the composed map, which is still a polynomial, but the degree will grow exponentially. So it will become more and more complicated once we start to iterate. So this leads to the definition of Fielding-Jula set. So the Fielding-Jula set of z squared plus c is the set of points in the complex plane such that these points do not go to infinity under iterations of the polynomial. And the Jula set of the polynomial is defined as the boundary of the Fielding-Jula set. So to give you an idea of what is a Fielding-Jula set and what is a Jula set, let's take the simplest example. So we start with f of z equals z squared. And then in this case, the Fielding-Jula set is the closed unit disk, because those are the points in the complex plane such that they do not go to infinity if you keep squaring the complex number, right? Because the modulus of those numbers is smaller than 1. And the Jula set for this polynomial is the boundary of the closed unit disk, namely, it is the it is the unit circle, right? So this is a very nice and simple example to give you an idea of what is a Jula set. But in general, Jula sets are more complicated. So here is an example. It's called Duality's rabbit. So the black region in the picture is the Fielding-Jula set. And the boundary of the black region, which is a superfractal object, this is the Jula set for a quadratic polynomial. And I have another example, which is called the basilica, because it looks like a basilica. So basilica is the Jula set or Fielding-Jula set for the quadratic polynomial z squared minus 1. Again, the black region in the picture is the Fielding-Jula set for z squared minus 1, and the boundary of the Fielding-Jula set, or the boundary of the black region, is the Jula sets. So these are two very nice examples of Jula sets, and we notice that they're connected. So in fact, we can also have Jula sets which are totally disconnected. So these are two examples where the Jula sets are just Cantor sets. So since it's a Cantor set, you cannot really see them. So these are points hidden inside these shining blue regions, right? So we have seen 4 examples So the first group of examples are Joula sets, which are connected. And the second group of examples are Joula sets, which are totally disconnected. So this dichotomy of connectedness of Joula sets is true for quadratic polynomials. That is to say, if you have a degree 2 polynomial from the complex plane to itself, then the Joula set is either connected or it is a Cantor set. But this is no longer true for polynomials of higher degree. And this connectedness dichotomy is also seen by something called the Mandelbrot set. So now we move to the parameter space. So we want to study the space of all the complex parameters C. So the Mandelbrot set is an important subset of the parameter space. It is defined as the set of all the complex parameters C such that the point 0 does not go to infinity under iterations of the polynomial f sub c, right? So in the picture, the Mandelbrot set is the darker blue region, which is a very delicate fractal object in the complex plane. So if we take c equals 0, like the very first example we saw, so c equals 0 lies in the center of the largest blob in the Mandelbrot set. So if we pick a parameter inside the Mandelbrot set, then the Joula set is necessarily connected. And if we have a parameter that is outside of the Mandelbrot set, then the Joula set is a Cantor set. So those are the second group of examples we saw earlier. Right. So what is a hyperbolic component? So very roughly speaking, so the darker region is our Mandelbrot set. A hyperbolic component is any blob shape or blob-shaped subset of the Mandelbrot set. So here, for example, I labeled by 1, 2, maybe I can zoom in a little bit, right? So I labeled by 1, 2, 3, 4, 5 to illustrate these are different hyperbolic components, right? So for today, our goal is to construct a Riemannian metric on every hyperbolic component of the Mandelbrot set. So let me just go back to the picture for a second. So for every hyperbolic component of the Mandelbrot set, we can think of it as a smooth two-dimensional manifold. And for smooth manifolds, we can consider a Riemannian metric, right? So it will turn out that our metric is conformal equivalent to the standard pressure metric. So I would like to remark that our result actually holds for more general hyperbolic component in the moduli space of rational maps. But in order to fit everything into a 30-minute talk, I will just tell you how to do this construction for a hyperbolic component of the Mandelbrot set. So I will start by telling you what is the standard pressure metric. And it is in the realm of thermodynamic formalism. So we start with an K by K matrix A, whose entries are either zeros or ones. So we also assume that this matrix A is aperiodic. That is to say, there exists a natural number n such that a to the power of n will be a matrix whose entries are all positive, all strictly positive. Right. So for such a matrix, it defines a one-sided subshift of finite type, and it is basically, which I denoted by sigma sub A, this is basically the space of sequences. So one sequence is denoted by I sub 0, I sub 1, I sub 2, blah, 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 where each I sub j is an element from 1, 2, 3, 4 to k, where k here is the k in K by K matrix. And one more condition is that I sub j is adjacent to I sub j plus 1 if the entry ij plus 1 in A equals 1. So basically this matrix gives us a space of admissible sequences. And this is one-sided infinite sequence. Right. So with this space, we can define a map, which is called the shift. So what does this map do? So if we have a sequence, I0, I1, I2, blah, 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 then apply this map to this sequence. This basically we just erase the first letter. So, or erase the first guy in the list. So we get I1, I2, and blah, blah, blah. So this subshift of finite type, sigma sub A, can be equipped with a metric as follows. We take two sequences, I and j, and the distance between I and j equals 2 to the power of negative n, where this big N is the minimum position where I and j differ. That is to say, this is the minimum integer n, such that I sub n is not the same as j sub n, but for all index smaller than n, so the sequence I and j are equal. Okay, so with this metric, then we can talk about Holder continuous functions on this subshift finite type, right? So now we consider a continuous function, phi, from the subshift finite type to the real numbers. And we saw the definition of pressure. So for such a function, we can define the pressure, and Mark gave a different definition, which is equivalent in the morning. So now we can define the pressure as the supremum of the things in the bracket. So this is the measure theoretic entropy plus the integral of phi on the subshift finite type integrated against this against an invariant measure. So here, H m sigma denotes the measure theoretic entropy of sigma, and this supremum is taken over all the invariant probability measures. Right. So we have seen a lot of nice properties about the pressure function in the morning, and we will see one more application of the pressure metric. So before that, let me just define equilibrium state. So given this variational definition for pressure, an invariant probability measure is called an equilibrium state of this continuous function if it is the measure which realizes the supremum in the definition, right? So basically equilibrium states is the realizer of the supremum. Okay, cool. So now we're moving to the heart of the first part, where we want to talk about pressure metric. So pressure metric was introduced by Kurt Mahoulan in around 2008. So what is a pressure metric? Well, we need to think about now Holder continuous functions. So we say a function phi from sigma to r is Holder continuous if it is alpha Holder continuous for some alpha between 0 and 1. So here is a quick reminder of what is alpha Holder continuous. That is to say, there exists a constant c and alpha between 0 and 1, such that for every two elements in the subshift finite type, we have that the distance between phi I and phi j is bounded by c times the distance between I and j raised to the power alpha. So this is basically the definition of Holder continuous. Right. Now we want to consider the space of pressure 0 Holder continuous functions on the subshift finite type up to some equivalence relation. So let me just explain a little bit more before I move on to tell you how the equivalence relation is defined. So basically, this is the space of Holder continuous functions, and the pressure of such functions equals 0. Okay, so the equivalence relation is called cohomologous. So if I have two continuous functions, phi1 and phi2, they are cohomologous if there exists another continuous function h from sigma to r, such that phi1 minus phi2 equals h composed with sigma minus h. And a continuous function is called a coboundary if it is cohomologous to 0. So basically, we consider pressure 0 Holder continuous functions on sigma up to coboundaries. So this is the cohomology classes of pressure 0 Holder continuous functions on sigma. Right. So now we want to understand, so what is the tangent space? So if I pick a point f, which is a cohomology class of required functions, then what is the tangent space, right? So you can calculate the tangent space at the class f in this space z sigma is the set of functions g, so that the integral of g against equilibrium state of f equals 0. And also this is defined up to coboundaries. Right. So the pressure metric, so this is basically a metric on the tangent space, or a symmetric bilinear form on the tangent space. So it is defined as follows. So now we take a tangent vector, which is g, right, as we defined above. So we take a tangent vector in the tangent space. Then I tell you the length of this vector square equals the variance divided by the integral of f against its equilibrium state. And what is the variance? Well, the variance is the second derivative of pressure. So in the in Mark's talk in the morning, we saw that the pressure function was real analytic, so we can take various derivatives of the pressure metric. So here we're basically considering the second derivative, right? So basically one can calculate, and this is what is called the variance, and it is indeed related to the variance in probability. Right. So this is a metric on the tangent space of this space z sigma, right? It is not quite a metric on a hyperbolic component. So now I'm telling you how we can construct a pressure metric on a hyperbolic component of the Mandelbrot set. So let's take
a simple question. Sorry. When you say it's a metric, do you know it's non-degenerate?
Yes, on this space, but yes, we will see later. It's not necessarily guaranteed on a hyperbolic component. It is non-degenerate.
Thanks.
Yes. So right, this is an excellent point, because if H is a hyperbolic component, we want to somehow pull back this pressure metric. And how do we do this? Well, this is because the dynamics, so for a point C in H, the dynamics of the quadratic polynomial restricted to the Joule set is hyperbolic. So by structural stability, if you move the parameter C in the hyperbolic component, then we will get a holomorphic motion of the Joule set, right? And in particular, for any two parameters C and C prime in the hyperbolic component, the dynamics are conjugate. So that is to say there's a subshell finite type sigma parameterizing the topological dynamics of the polynomial on its Joule set. So now we want to consider a thermodynamic mapping, which maps the hyperbolic component into the space of Z sigma, where the sigma is the sigma parameterizing the dynamics on the Joule set. So if we have a parameter C, we send this parameter to the class, to the cohomology class of delta of C times log of FC, log of the absolute value of the derivative of the map. So where delta here is the Hausdorff dimension. So delta of C will give us the Hausdorff dimension of the Julia set for the map F sub C. Right, so using this map, we can pull back the pressure metric to the tangent space at C in the hyperbolic component. So how do we do this? Well, we take a path in the hyperbolic component with the starting point being C, and the derivative of this path is the tangent vector in the tangent space in TCH, right? So we can basically just define the length of the vector as the length of the image of the vector in Z sigma, right? Because for Z sigma, the pressure metric is well defined, so we can basically just pull back the metric to define a length for a vector in the tangent space in the hyperbolic component. So basically the resulting metric is the pressure metric on hyperbolic component. Right, so any questions? Yeah, and so far now, we do not know if the metric is degenerate because this thermodynamic mapping, although the metric on Z sigma is non-degenerate, but the mapping may map something to a zero cohomology class, right? So this is actually this is the most difficult part of the work. Okay, so now I will start to telling you how to construct our metric. So if H is a hyperbolic component, then for any parameter C in the hyperbolic component, we will denote by M sub C the set of invariant probability measure on the Julia set, and we will equip M sub C with the weak star topology. So these are standard things about invariant probability measures. So now, if we take a point C sub 0, you can think of it as a base point in the hyperbolic component. Then there exists a neighborhood, which I denote by U of FC0. So this is a neighborhood of C0 in the hyperbolic component, such that there's a well-defined quasi-conformal map conjugating the dynamics of FC0 to FC for every C in the neighborhood of C0. So this quasi-conformal map basically comes from the holomorphic motion. Right, so now I want to define a map on MC0 cross the neighborhood into R as follows. So M takes two input. So the first one is an invariant measure on C0, and the second is a parameter C in the neighborhood of C0. And the M mu C equals this integral. So what does this mean? So first we take this invariant measure mu and we push forward by this quasi-conformal map so that it is a invariant measure on the Julia set J of C. So this is the Julia set associated to the parameter C, and we integrate the geometric potential, which is log of the absolute value of the derivative of F sub C against this pushed forward measure. Right, so this map has some nice properties. So first of all, if we fix the first coordinate, so we fix mu, then this map is a map from the neighborhood to R, right? So this map is harmonic. If we fix the first coordinate, it is harmonic, and therefore it is real analytic. And also, if we think about this map M as a map where, so the induced map M prime I wrote here from the space of invariant measures into the analytic map from U from this neighborhood to the real numbers. So if I give you a measure, then this M prime spits out a map which is real analytic. So the induced map M prime, it is continuous with respect to the C star topology and the real analytic topology on the real analytic maps. Right. So now we want to consider a particular measure for the function we defined
Could I ask
before.
a question?
Yes.
What was the M on the previous slide?
Oh, so this big M is the function we defined here in the middle of the slide.
And what's the mathcal MC0 again? Sorry.
Oh, sorry. This is the space of invariant probability measures on the Joule set JC0.
Oh, yeah.
Yeah, sorry, there are too many M's. Okay, right. So now, right, if we recall this map, so we want to insert a particular invariant measure mu and consider the map again. So this particular map mu we want to consider is something I denoted here by mu bar. So this is the equilibrium state of the following pressure zero Holder continuous function. So this is basically you take the negative of Hausdorff dimension times the geometric potential. So this is a map from the Joule set into the real numbers. And mu bar is an invariant measure on the Joule set. Therefore, we can consider the function m sub mu, which is the previous function where you fix the measure to be mu bar. So this is what I call the multiplier function, just to give the function a name. Right, so here, just for convenience, I wrote down the definition for the multiplier function m sub mu. So m sub mu of c equals this integral. So this is basically just push forward the equilibrium state, and we integrate again, integrate the geometric potential against the pushed forward measure. And in particular, this multiplier function is real analytic. Right. So now here comes the key proposition for our construction. So if we fix a base point C0, and then for any other points C1 in the neighborhood, we have the following inequality. So what does this inequality say? So the inequality is about the relationship between the value of the multiplier function at C1 and C0. So what is really this value, right? So this is basically the Lyapunov exponent of those measures. So this is basically you can think of it as the Lyapunov exponent of this equilibrium state versus the Lyapunov exponent of the push forward guy. But the push forward guy is pushed forward by a conformal, quasi-conformal map, phi sub c, right? So this is basically, we're measuring, so the quotient on the right-hand side is a way to measure how much the Lyapunov exponent is distorted by this quasi-conformal perturbation, right? And this proposition is basically saying that this distortion is bounded below by the ratio of Hausdorff dimension, right? And also you can reverse the role of C0 and C1 to get another, to get an upper bound, but yeah. Right, so this key proposition will enable us to construct a symmetric bilinear form on the hyperbolic component. So now we consider the function which I call g sub 0. So this is the function from the neighborhood of C0 to the real numbers. And for an input parameter c, this function will spit out delta of c times the value of the multiplier function at the point c, right? And from previous result, we know g sub c0 is real analytic because the Hausdorff dimension function is real analytic, and we know the multiplier function is real analytic. And we, moreover, we know that gc sub 0 has a minimum at the point c equals c0 because of our proposition before. So this is to say C0 is a critical point of GC0. So now, because C0 is a critical point, so the Hessian of this function GC sub 0 is well defined. So now we can basically take the second derivative of GC sub 0, right? And this gives us a symmetric bilinear form on the tangent space at C0 of the hyperbolic component, right? So I can basically just define the length of the tangent vector square equal the second derivative of GC sub 0, right? And what are some of the properties? Well, this by a symmetric bilinear form has the following properties. So this is conformal equivalent to the pullback of the pressure metric on the hyperbolic component we discussed before. And more importantly, this metric or metric is non-degenerate on the hyperbolic component, and therefore it defines a Riemannian metric. So as we said before, a priori, we do not know if the pressure metric is degenerated or not, and this is basically the most difficult part to find out if the pressure metric is non-degenerate, or you find out in which direction, in which tangent space, in which direction the metric is indeed degenerate. So there are other related works where people construct measures in similar spirit for different other spaces. To name a few, there are works of Bridgman-Taylor and Kurt McMullen and Mark and Sharp, and Bridgman, Canary, Labrie, and Sabrino. So basically, Bridgman-Taylor constructed a similar measure for the so-called quasi-conformal space in the theory of Kleinian groups. So in their setting, in quasi-Fuchsian spaces, the pressure metric is degenerate, and they found out which direction the pressure metric is degenerate. And also in the work of Bridgman, Canary, Labrie, Sambrano, they studied pressure metric for a space of announced representations. So that is a space in character varieties in higher Teichmüller theory. And there they also have degenerate directions for the pressure metric, right? And it's also very interesting if we indeed have degenerate directions, because that will say something more about the intrinsic geometry of the character variety, or the manifold you are considering about, or they also imply the specific, so the specific or the related manifold, the geometry of three manifold, or the geometry of symmetric spaces associated to those representations. Right. So as we note from Mark's talk in the morning, if we consider the pressure function, it's naturally related to Hausdorff dimensions, right? So actually, Hongming and I started this project with the goal of understanding Hausdorff dimension function on hyperbolic component. So with our current work, we know the Hausdorff dimension function does not have local maximum on any hyperbolic component. And this is also proved by Ransford with analytic method. And still, we do not know much more beyond that. But here is a picture from a paper of Baudat and Zinsmeister, where they had a computer graph. So they did the calculation numerically and plotted the Hausdorff dimension. So basically, for example, we want to understand the critical point of the Hausdorff dimension function on the main cardioid of the Mandelbrot set. So from their picture, it looks like the Hausdorff function, or the Hausdorff is ball shaped. So that is to say there's no critical point in the main cardioid. But I think the proof of this fact is very hard. And I hope this will inspire more people to work on the problem and maybe continue what we have been doing. And I would like to thank you for your attention.
Let's thank our speaker. And we do have time for a couple of quick questions, but any longer questions, Mary will be available in the breakout rooms after our next lecture, so or after our next talk. But quick questions.
Can I ask some questions?
Yes.
So do you have any result related, like incompleteness or something like that, like the estimate of the pressure metric?
The answer is no, but I think the pressure metric is incomplete. Yes.
Yeah, incomplete is a lot of work to do.
Right. So basically, like the completion will basically lie on the boundary of the hyperbolic component, but it could be some special subset of the boundary. Yes, that is a very interesting question.
So you also have something like a rigidity result, right? So you have the ratio of the Hausdorff dimension is multiplied by the Lyapunov exponent. Do you have the rigidity? Like you only know the equality happens if and only if that C has to be C0.
I think so.
That coming from the minimum thing,
Yes,
you just
yes.
computed it, right? Yeah. Another just very broad questions, like what about for a non-hyperbolic component? Like, are there any possibilities to do things like that?
Yeah, I think this construction may or may not work, right? Because here we want to take the second derivative of pressure, kind of, all right. Let's see. Yeah, so I think maybe for, yeah, so from the pressure perspective, so maybe pressure is not differentiable or twice differentiable for some not hyperbolic systems. And from the Lyapunov exponent perspective, maybe the key proposition, the inequality, may not be true for some non-hyperbolic systems. Yeah, that is definitely very interesting. And I think it requires some like thinking or proof before just like precisely state. Yeah.
Sure, thank you.
So I think we'll stop there, but like I mentioned, Mary will be available in the breakout rooms where you can ask more questions. And we do want to get prepared for our final talk of the day. But let's thank Mary again for a very nice talk.